There are scientific problems so tough that people started calling them impossible. For over a century, mathematicians threw everything they had at one of them and still came up empty. And yet, in just the past few months, an AI stepped in and did what no human ever could, opening the door to a discovery that could change how we predict weather, build aircraft, and even understand the very physics of our universe. Alright, so for decades, some of the math behind this has been stuck in a deadlock. Mathematicians have tried and failed to solve certain equations. And these problems are so infamous that they're actually listed as one of the 7 Millennium Prize problems. Solving just one of them wins you $1 million. That's how unsolvable they seem. But now, an AI from DeepMind has done something nobody else could. It didn't just crunch the numbers faster, it uncovered entirely new solutions to these equations. Solutions that human mathematicians later confirmed as correct. And to really appreciate how insane this is, we have to step back for a second. The core of this problem lies in the Navier-Stokes equations. These equations describe how fluids, things like air, water, even gases, move and behave. If you've ever looked at the trail of smoke rising from a candle or the turbulence on a plane ride, that's Navier-Stokes in action. They're partial differential equations, or PDEs, and they're notoriously difficult. What makes them especially nasty is something called singularities, also known as blow-ups. That's when values like velocity or pressure suddenly spike to infinity in the math. Obviously, you don't see infinite pressure in real life, but these scenarios help scientists understand the limits of the equations and where the models start to break down. The idea of proving whether these singularities actually exist in the three-dimensional Navier-Stokes system has stumped people for over 150 years. To give you an idea of how fundamental this is, it impacts weather prediction, aircraft design, naval engineering, even astrophysics. Better models of fluid behavior could mean more fuel-efficient planes, more reliable climate simulations, and even insights into planetary formation. So, yeah, the stakes are massive. What DeepMind did was take a totally fresh approach. Instead of just brute-forcing simulations with a supercomputer, they turned to graph neural networks and something called physics-informed neural networks, or PINs. Now, unlike normal neural nets that just learn from giant datasets, PINs are trained directly on the equations themselves. Their output is constantly checked against what physics says should happen. And by minimizing the residual, the tiny gap between what the AI predicts and what the actual equations demand, they get closer and closer to a true solution. The result was groundbreaking. A machine learning model uncovered entirely new families of singularities, ones that had never been described before. Mathematicians from New York University, Brown, and Stanford later stepped in and confirmed the results, proving that the AI's discoveries were mathematically solid and not some glitch or trick of computation. In other words, this wasn't an AI hallucination at all, but a real discovery that could be fully verified. Now, one of the most fascinating parts is how the AI uncovered patterns within these blow-ups. So, when fluids blow up in the equations, you can characterize how fast it happens using a number called Lambda. DeepMind system noticed that as the singularities became more unstable, there was this surprisingly clear pattern when you plotted Lambda against the order of instability, the number of unique ways the solution could deviate from the blow-up. They saw this in the incommensurable porous media equations, the Bussesque equations, and of course the Navier-Stokes. That regularity suggests there might be a whole landscape of other singularities out there just waiting to be uncovered. And the story gets even stronger from here. These singularities that the AI found aren't stable, and in this context, stability means whether a singularity holds up. Even if you tweak the conditions a little, a stable singularity is robust. You nudge the setup, it still happens. An unstable one requires crazy precise conditions. Mathematicians have long suspected that for the boundary-free three-dimensional Euler and Navier-Stokes equations, stable singularities simply don't exist. That's why finding unstable ones is such a big deal. They might look fragile, but they reveal deep truths about the structure of the equations themselves. And the level of accuracy they achieved here is just mind-blowing. We're talking errors so small that researchers compared it to predicting the diameter of Earth and being off by just a few centimeters. That's the scale of precision they're working with. To get there, They used advanced machine learning techniques like second-order optimizers during training, pushing these networks closer to machine precision than anyone thought possible. That's what allowed the AI to capture such delicate, elusive solutions that traditional methods couldn't reach. The visuals they've put out make it easier to wrap your head around. For example, they mapped out vorticity fields, basically how much the fluid is spinning at every single point. You can literally watch how these unstable singularities evolve, slice through them in one-dimensional sections, and see the progression as instability increases. These are the kinds of detailed views that weren't accessible before. Obviously, DeepMind didn't do this alone. They worked with mathematicians and geophysicists from leading universities to check the results and ground them in existing theory, which is why the discovery is being taken as a serious breakthrough instead of just another AI headline. What makes this historic is that AI is acting like a research partner, pointing mathematicians to solutions they couldn't reach on their own. Yang Wang, one of the lead researchers, put it pretty bluntly. By embedding mathematical intuition into these neural networks and driving them to extreme precision, they essentially transformed pins from problem-solving tools into discovery engines. This changes the way proofs are done. Traditionally, mathematics is built on logical reasoning and human ingenuity. With computers maybe helping check the grunt work, now with AI in the mix, we're entering a new era of computer-assisted mathematics. These systems can navigate landscapes of equations that humans couldn't realistically explore, flag potential solutions, and then let human experts step in to verify. This breakthrough reaches far beyond mathematics. In meteorology, it could sharpen storm forecasts. In aeronautics, it offers a path to cutting turbulence and fuel use. And in astrophysics, it connects to phenomena like black hole disks and interstellar gases. At the same time, it shows AI stepping into fundamental science, tackling problems that resisted centuries of effort and expanding what research itself can achieve. And yeah, with breakthroughs like this, there's always that mix of excitement and unease. Because when an AI starts solving problems that were once thought impossible, it shows both the potential and the vulnerability of the technology. Some people in the tech world, like Vitalik Buterin, have already voiced concerns about how to secure AI's development responsibly. The fear is that the same power that can unlock scientific frontiers can also spiral in ways we don't fully control. Still, for now, the focus is on what just happened. A century-old mystery in fluid dynamics cracked open by an AI leading to discoveries that have already been mathematically proven. A problem once called impossible is now a playground for machine learning models. And that's not an exaggeration. It really does feel like the start of a new era. All right, that's all I've got for today. If you found this as fascinating as I did, let me know what you think in the comments. Drop a like and subscribe for more. Thanks for watching, and I'll catch you in the next one.